Yeah, exactly. Let's start. So, Jay, thank you very much for accepting to give this seminar, this speech in this cycle. And as you know, that is a very important and hot topic. So please, Chris already told you, usually we spend 45 minutes, let's say less than 1 hour for the presentation in order to have time for questions and discussion. But
okay.
I repeat what Jay also suggested to everyone. If we have any questions, we can ask even during the presentation for clarifications and for discussion. So Jay, please.
Okay, thanks. I called this talk, How Does Friction Start? I would call it How Does Earthquakes Start, but then we'd get into controversy on the first statement. So this is an experimental talk, so I'll just talk about some rather new experiments that we're doing. And the person that actually did all the work is my graduate student, Shachar Gewirtzman. And here it goes. So anyone that's heard me talk about this stuff in the past few years has seen the same picture, but it's two blocks pushing. We're looking at two blocks pushing against one another, and we're interested in we're interested in this problem, the problem of an earthquake. But what we're really studying is this problem: how the interface that separates two elastic, rather smooth but still rough blocks, how it separates, how we break the contacts along this interface. And over the past few years, we've done a bit of work about showing that, at least in our experiments, the process of breaking this plane of contacts is by way of cracks. So you have ruptures or earthquake-like things that are moving in either way, and as they move, they break the contacts until when they finally break the whole line of contacts, we get macroscopic motion. So yeah, we know a lot about cracks, and our group, as well as quite a few others now, have seen such things. So now we're switching gears and asking about how the cracks form in the first place, and that's the nucleation problem. So we'll be looking at how we start the initial cracks that then propagate and have earthquake-like behavior. See, I'm trying to be very politically correct here, Chris. Okay, so what actually initiates frictional motion is the process of creating this initial crack that then moves and propagates at sound speed, super shear, or whatever you'd like. So we'll be talking about these nucleation fronts, but first I'll give you a little bit of background about the rupture fronts that they form. Now, I know that many of you have heard Elza Bayart's talk a few weeks ago, and there might be some overlap even in the slides because we work together a lot. So if there's, I wasn't able to attend that talk, but if there's a lot of overlap, it's time to go to sleep or something and wake up when we get to the newer stuff. And even if there is a bit, I'm sure that Elza had much smarter comments than I'll give. So whatever, let's continue. Okay, so often when we think about friction, we think about a friction coefficient. And the friction coefficient is basically was explained by Coulomb and Amonton about 500 years ago, or described by Coulomb and Amonton about 500 years ago, but it was actually explained only recently by Bowden and Tabor in the 50s and 60s of the last century, when they realized that even if you have nominally very flat surfaces, the surfaces themselves are actually quite rough. So the real area of contact, which we'll call A here, is orders of magnitude smaller than the nominal area of contact between the two plates. Well, what does that do for you? Well, each contact then is subject to huge pressures. So if you have, in fact, these pressures approach the hardness of the material. And so the material actually starts to flow along the contacts, and these huge pressures will actually increase the net area of contact, or the real area of contact. So the real area of contact is, in a sense, a dynamical variable. It changes. It's not constant during this process. Now, the friction law is basically that the harder one presses the normal press, the normal force, the more area of contact is being formed in this way. So the real area of contact is proportional to the normal force that we're applying. And slip only starts when we push hard enough so that we break these contacts across the interface. So if we put, so slip starts when the shear force equals the area of the real area of contact times the shear strength, and putting these two together, we get the static friction coefficient, and we get an explanation for why more or less it's order 1, because it's basically something like the shear strength divided by the yield strength of the material. Now, I don't have a problem with this. In fact, I don't have a problem with anything here except on how this contact area breaks, because if we break the area of contact, I mean, this picture tacitly assumes that all of the contacts are being broken exactly at the same time, so they're all simultaneous. But we know that's not really how things break. In general, materials break because cracks propagate through them. So the fracture process doesn't break all of these contacts at one time, but sends an earthquake-like front through the material, and that's responsible for breaking it. Now, this has a lot of ramifications on the friction coefficient, on the whole friction process. And as we'll show in a second, what we're one result of this is that the static friction coefficient of any given material isn't a characteristic property of the material, but rather it depends on the small details of how these materials are placed together. Okay, so the onset of friction in this picture is basically the question of how, when, or why cracks propagate. So things break, as I said, because cracks propagate through them. That's a general statement. And the reason is, and I apologize for if I'm just repeating stuff that you all know, but any crack, however small it's going to be, will focus stress at its tip. And that stress approaches a mathematical singularity. So the stress field at the tip of a crack, here I'm showing tensile cracks, but it's the same for shear cracks, scales as 1 over the length r from the crack to the power of to the power of 1/2. So as r goes to 0, the stresses become infinite. So basically, the claim is, and I'll show you some data that will back this up, is that the slip of interfaces or frictional motion is actually caused or mediated by shear cracks, or in the jargon they're called mode 2 cracks. Yeah.
Jay, can I ask you a clarification?
Sure.
Okay, so which is the origin of the singularity? Is because we are using elasticity everywhere except at the tip? So is the singularity a real physical feature, or it is a feature derived by our assumptions?
Okay, it's a mathematical feature if you assume elasticity everywhere and a stress-free and in back of the crack where we relieve the stresses. Now in frictional cracks, we haven't relieved all the stresses. There's a residual stress in back of the crack. But if this residual stress is more or less a constant, because we're looking at a linear system, we can subtract it away. So we're actually in the same, we're solving the same problem as for a stress-free crack in the back. Now, Mathematically, if you'd like, you can think of this as a branch cut. So the system has the topology of two branches, and that will give you automatically an r to the 1/2 singularity. You have two solutions on the same plane. A solution above the cut and below the cut. Physically, we don't need linear elasticity, or any kind of elasticity will hold. Now, do we really get this stress singularity? The truth is not. I mean, the difference between a material that's tough, like steel, and a material that's very brittle, like rock or glass, is basically how the material regularizes this approach to singularity. That's called the process zone, and I won't talk about that a lot, but I could, if you wish. I don't know, did I answer your question?
Yes, you answer. But I would like to focus that in any realistic material which is not elastic, we might assume that in reality, we might not have the singularity.
Well, I think far enough away, all materials are more or less elastic, unless we look very hard. So away from the crack, we have very small strains on the material. Now, as we approach the crack, the constitutive law may change. So, for example, we've seen that if one looks not at the strain law as linear, but you add a quadratic term, you'll still get a singularity here, but the singularity will be of a different character. It'll be r to the -1. So it's actually, in that case, a stronger singularity. So I think that far enough away, like if we have, this singularity will take place if we have a condition that's called, in the fracture literature, small scale yielding, where all the dissipation can be confined to a very small region around the tip of the crack. Now, how small is small? If we're talking about the tectonic plate, so maybe small is a few kilometers, but we're looking at scales of 1,000 kilometers. So it's still, we're still approaching this singularity. Now, the material, as we get closer and closer, might behave differently. But so long as all of the dissipation can be confined to some region that's relatively small compared to the scale of whatever we're considering, we'll still find this stress focusing that will approach a singularity. So I hope that's clear.
Yeah, thanks, excellent.
Okay, thanks. Anyway, this was a great example of what I want from you guys. Or people, I mean, just bother me. If something is not clear, or if you want to discuss a point, just stop and we'll talk about it, because it's often these questions are more important than what I wanted to get to in the first place. So anyway, the formalism of talking about what cracks do and how they do it is basically fracture mechanics. So I'll show you that fracture mechanics works to explain quantitatively frictional cracks and describe their motion. But first I'd like to explain a little bit about our experiments. Now, Elsa has probably told you about this, so I'm going to go through it quickly. We mentioned that we're interested in the real area of contact along this spatially extended interface, and these are the dimensions of the experiments that I'll be talking about, more or less. Now, we visualize the whole contacting surface at one time by shining a sheet of light at an angle that's beyond the incident angle for total internal reflection between the transparent material that we're working with and any air that's trapped between asperities or between contacts. So anytime basically this light hits an air pocket, or not a contact, it's reflected away from the interface. and light only goes through this area of contact at or very near to the points of contact. So if we look at the light that's transmitted, it's more or less proportional to the real area of contact along the interface. And we're taking pictures of the interface at around 600,000 frames a second. So if our cracks are moving at order of 1,000 meters a second, so every millimeter or so, we're taking a snapshot or we're mapping the real area of contact along the entire interface in these experiments. Now, what do we see? We see something like this. So this is a map of, this one is actually a section of the real area of contact somewhere in the center here. And what you see is the hot colors are high contacts, the cooler colors are low contacts. And in order to be able to see clearly these rupture fronts that I'll be talking about, we normalize these to the value that they had before anything started. So to go back, this is the raw data that we see, and this is in 2 dimensions. This is just a picture again of the real area of contact along the 2-dimensional interface here. When all of these points are normalized by their values at the beginning of an experiment, then we get something that looks very homogeneous. And here, this is a picture of a front that's moving. The hot colors are contacts that haven't been disturbed. And in back of the front is moving like this. These are the broken contacts. And this is just a few snapshots of a front that's moving at around 1,000 meters a second in these experiments. So we actually see the fronts moving. And in order, and I'll be showing you for the beginning of the talk at least, an integrated, so each one of these things is a 2-dimensional map at each point in time, but to make life simpler, we're going to integrate across this thickness dimension, like so. And so I'll be showing you maps like this. So this kind of ugly orange color is the initial contact area already normalized to its initial value at some point here in time, which we'll call 0. And our time will usually be, time will be in the vertical axis, the spatial coordinate will be in the horizontal axis. So this is our front that's propagating through the material, and the higher the slope, the slower the front is going. So this is a front that started at one of the edges of the system over here, and then is propagating slowly, picking up speed until eventually it gets to near the Rayleigh wave speed, which is the speed limit for standard shear cracks. And we supplement these measurements of the real area of contact by strain measurements. What does that mean? We take very minute strain gauges. So each one of these green squares is a strain gauge that's situated a few millimeters, 3 millimeters or so from the contact region. Each one of these strain gauges is a rosette strain gauge. So it gives us all of the strain tensor at each point. These are separated by 10 millimeters or so. So basically, and we're measuring the strains at 1 megasample a second, so 1,000,000 times a second, each one of these coordinates separately, which makes for a lot of wires in this experiment. And so we're getting, as the fracture or as the rupture moves across the sample, at each point here, we're getting the strain measurements that the rupture is causing.
Jay,
yeah.
Quick question. Sure. Does the strain tensor setup interfere with the light transmission or reflection?
No, that's why we have it a few millimeters above the interface. So the light is moving underneath well, 2 things. One, we can, if our incident, if the side where the strain gauge is situated is on the incident side, so the light goes underneath them, and because they're moved, they're separated by a few millimeters, the light actually comes out underneath them if we flip the sample around. So we're not seeing the strain gauges in the light measurements.
Thank you.
Sure. Okay, This is a typical stick slip measurement. So we have this is at a scale of seconds. So we're pushing at the shear force. We get to some peak. It then goes down. Then then we continue to push. Now we're pushing at a constant constant velocity here. So we get stick slip motion that you're all familiar with. Now what we're interested in is actually the motion around one of these, each one of these stick slip points, the point where the interface breaks. So we're going to focus on the fast processes at around each one of these peaks. This is a real experiment. So this is the real area of contact at second resolution. So there's 7 seconds between one stick slip event, which we see here. This is a rupture front. And the next one, which is the next rupture front. Now, if we zoom in on each one of these, say this one here, so at the microsecond time scale, we see this the rupture fronts that I was showing you before. So if we zoom in around each one of these areas, then we see earthquakes or lab quakes or something as they propagate. And again, we're integrating along the thickness of the sample. So we'll be looking at maps like I showed you a minute ago. So each horizontal line is basically a snapshot of the integrated real area of contact across the interface. So we're actually looking, as long as an earthquake is on one strand or something, we're looking at something that's pretty analogous to real earthquakes. Now,
Jay,
yeah.
Jay, sorry, can I ask you a question? So
sure.
in this picture, when you measure the propagation of the rupture front, so when you say crack-like, is because the slip velocity has a sort of Kostrov type function?
No, I think, yeah, I'll show you in a second, but you can describe all of these ruptures as shear cracks, identically as shear cracks.
Okay, so here you don't have any cohesive zone.
We do have a cohesive zone. We actually measure it, but not in this talk. So we're actually measuring different cohesive zones in different types of materials right now. Oh, my postdoc is doing it. I don't do any work. I just watch them work. But so okay. we can look at the structure of the cohesive zone, but I won't be talking about that today.
Okay, thanks.
Jay, one more quick question while you're on this slide. So this picture on the top left here, what happens before 319? Is that like the first stick slip event? Is that why there's a longer period where it's really stuck?
Right, that is exactly this period. Right. Okay. So we're loading. We normalize the data to around at this point or so. Okay. And that's why it's this homogeneous shade of orange or something, because nothing happened. And now we can actually see aging here, if you like.
Right.
So we broke this contact area. It's now blue, or we've reduced it by 20-30% or something like that. Mm-hmm. And within a few seconds, it already approaches its value at the beginning of the experiment. Mm-hmm. And then it breaks again.
Yeah, cool.
So, okay, thank you for these questions. This is great.
Thank you. Yeah.
Okay, so as Massimo hinted, we're going to explain all of this stuff, describe all of this stuff using fracture mechanics. So for those of us who aren't experts in fracture mechanics, I'll tell you all that you need to know in order to understand this talk. So first of all, assuming that we have a linear elastic material, both in tension or in shear, the stress field at the tip of a crack, it scales as K, which is called in the jargon it's called a stress intensity factor divided by the distance r from the tip itself, so that the stresses are singular. And all the components of all the different components are all singular here. Cracks move not because the stresses become infinite, but because the energy flowing into the tip of the crack is exactly enough to balance the dissipation that's caused by breaking a unit area of material, and that's called the fracture energy. So even if a crack is stationary, we still have this putatively stationary singularity, but it doesn't transport enough energy to break bonds. So actually the energy balance, or the balance of energy, is the criterion for getting a crack to move. Once the energy flux into the tip of the crack goes beyond what we need to break things, then cracks start to propagate, and earthquakes as well. And the earthquakes that I'm talking about have a speed limit. So these are the sub-Raleigh earthquakes, if you want, or fractures. And the speed limit for these is the Raleigh wave speed, or the speed at which a disturbance moves along a free surface. Shear cracks can also go faster than that, but that's not relevant to what I'll be talking about today. Okay, now we're going to compare. Okay, these wiggly colored lines are measurements of each one of the components of the strains that we're measuring in front of the crack. So we have our strain gauge that's nearby our interface, and we're looking as a function of the distance of the crack tip to the strain gauge at how the strains behave. So these are the XY, XX, and YY components. X is the propagation direction, Y is the normal direction. Okay, and we see a bunch of colored lines. Great. Okay, now if we take fracture mechanics and we fit now the only free parameter here, which is the stress intensity factor, this K, well, if I fit it to here, I can get this black line is exactly the prediction that fracture mechanics would predict. Now, why aren't we seeing the singularity, or something that goes to infinity? Because our strains are off axis. So we're not going to R equals 0. We're looking as a function of R and theta. But even when the crack goes right underneath the strain gauge, it's still separated by a few millimeters, and that's why we see this wiggly function. The wiggly function is a universal function predicted by fracture mechanics that goes along with this singularity. Now, I have a problem here if I'm just curve fitting, because I have one free parameter and I have a tensor which has 3 different components, and now it's time to put my money where my mouth is, and this is what Ilya Svetlitsky, my former graduate student, showed. With one free parameter, we fit all of the tensor components. So this does a phenomenal job with only one free parameter, the stress intensity factor, of fitting all of the strains or stresses that we measure. Now, the stress intensity factor can be translated to the fracture energy using the formalism of fracture mechanics. So by measuring this K and knowing the velocity, because we're watching the crack as it's moving, we basically measure the fracture energy, or the energy to create a unit surface, a unit extension of this rupture. Now, in these experiments, the fracture energy is actually proportional to the normal stress, the normal force or stress that we're applying. In these experiments, it's 1 joule per meter squared. I'd now like to talk about the equation of motion for frictional ruptures. So remember, I talked to you about energy balance. So the energy flux going into the singularity has to equal the dissipated energy, or the fracture energy. And this is kind of a cartoon of fracture mechanics. This is what it's saying. So the energy flux, which we'll call G, has 2 pieces to it. Don't worry if you're not following details, because I don't care right now. I'm just showing you that we can do this. So this is separable under certain circumstances, and this static stress intensity factor, probably, as Elsa Bayer told you a few weeks ago, can actually be explicitly calculated by the stresses in front of the crack. The fracture energy we can measure by fitting any one of these stress curves to LEFM. So this is a measure of the fracture energy. And this thing, which little g is a universal dynamic function, which when we invert it is actually the equation of motion for an earthquake. If I want to, CF is the instantaneous velocity of the crack. I know what this is for every crack length L. I know what this is because I've measured it. If I put these two together, I can get a prediction for how the velocity of the rupture changes, for example, with the length of the crack. And I can also get a prediction for crack arrest. And I'm going to go through this really fast because Elsa probably talked about it. And this is not really what I want to talk about. But this formalism, for example, will tell us when a crack will arrest. So this is an example of a crack that started over here, a rupture that started over here. It arrested at this point. We measured the point at which it arrested, and we can predict it by calculating the static stress intensity factor. And this is a comparison of the predicted length of arrested cracks to the measured length. So this is work that Elsa Bayer spearheaded, and we can show that if we can measure the stresses ahead of the crack in the laboratory, we can certainly predict an earthquake's magnitude. And that's what this is showing. Now, beyond that, we can predict its motion. So these are a number of experiments under identical conditions. We're looking here at the shear stress that we're applying for a constant normal stress. And we see that, and these are the shear stresses along the interface that we're measuring with these strain gauges for a bunch of different experiments right before rupture occurred. And you can immediately see here that we have a large spread of the shear stress for the same normal stress. Each one of these systems, each one of these experiments was stable. Okay, so the integrated value of this delta tau over the area gives us the shear force that we're applying. That divided by the constant normal force that we're applying is the static friction coefficient. As you can see here, there is no real characteristic value of the static friction coefficient because, what happens at different stress values? For example, this guy here, we're barely over 0 of delta t at some points, and it's kind of moving along slowly, even decelerating. This guy here, where we've overstressed the system from here to kingdom come, immediately jumps to its limiting velocity, which is the Rayleigh wave speed, and here are all the intermediate cases. So the difference in the dynamics between all of these is here. Now, if I take our equation of motion that I just sketched for you, invert it, and look at the prediction now of what the equation of motion should look like. So I'm going to take all of these data, and these data, and then derive from each one of the experiments this universal function. That's what I'm showing here. So this is the universal function of fracture mechanics that describes quantitatively all of these experiments. So fracture mechanics works amazingly well and quantitatively. There are no free parameters in this theory. Everything is measured. So we have a wonderful prediction for each one of these initial shear profiles of exactly how an earthquake is going to propagate. And we can get slow earthquakes, for example. These are very, very slow earthquakes. And in these cases, this one here and this one here, we're just barely over. We're barely over the necessary stress to get to the fracture energy. For those of you who aren't experts in fracture mechanics, this should be confusing as all get out. So I'm going to take a second just to say something. This little g, which is derived by fracture mechanics, is in a sense an efficiency function. So it's telling us how much of the strain energy we've put into the sample by shearing it, how efficiently it's transported to the tip of the crack. as the crack approaches its limiting wave speed or limiting velocity, this efficiency function actually goes to 0, which is why at each moment in time, all of these points are exactly, this is exactly the energy that arrived at the tip of the crack is exactly equal to the fracture energy. And that gives us our equation of motion. So it took me, when I was getting into this business, a while to understand this. So I'm trying to share these this craziness with you. So,
Jay,
yeah.
Jay, can I ask you a question?
Sure.
So therefore, if I interpret the equation of motion, the way in which linear elastic fracture mechanics formulates the equation of motion, this implies that because you are measuring a strain energy, this means that it does not care the type of dissipation. So it can put any type of dissipation, even it is not necessary that the dissipation will be on fault. It is only necessary that will be inside the process zone, because we have the small scale yielding. So
that's true. All the dissipative processes are given by this function, gamma. But we don't know a priori where it is, and it doesn't need to be at the tip of the crack. It can be 100 meters away from the crack.
Yeah, but therefore, the reason why I am doing this comment is twofold. First, because it is important when later on we will discuss the extrapolation to earthquakes. But it is also important for terminology, because this means that the classic definition of Griffith of fracture energy, even here, is much more general. Even in linear elastic fracture mechanics is more general, because it can be any type of dissipation, not necessarily just a surface advance.
Exactly, exactly. In fact, this, as long as we're far away from the tip, we have no idea what the dissipative mechanisms are. And they're all lumped into this one variable. Now, when does this break down? This breaks down if we have large bulk dissipation, or if we get close to the crack tip where we're actually seeing bulk dissipation take place. And then all of this has to be regularized. But as long as we're far enough away, we can't say, we don't care where this comes from, as you said.
Excellent, thank you.
Okay. Now, this is telling us, okay, this is just an advertisement showing that there is no such thing as a static friction coefficient. These are, for the same two blocks, these are measured static friction coefficients. In experiments that we did a number of years ago, you see that they can change by at least a factor of 2. Now, these sharp lines here are experiments where we've exactly duplicated the conditions of the experiment. So you can get a very well-defined friction coefficient, but it's a nowhere general. You change a little bit, even the initial angle of the two plates by 1/100 of a degree, so you can go from here to here. So, but if we want to predict what the friction coefficient is, this is what brings us to the subject of this talk, actually. How much time do I really have? Whoever's running this, Chris or Massimo.
Yeah, but Jay, I mean, we would like to finish in 45 minutes. So
okay.
45 minutes, I don't know, because we're having a discussion. And that is another reminder for everyone on this call to interrupt with questions. Don't wait until the end.
Okay, but how much time do I have? I can jump forward and get to the nucleation part. I haven't talked about nucleating.
No, you have 40, 45 minutes, Jay, so go ahead.
It's 1:15. We're hoping to end by the hour, but yeah, plus or minus.
Okay, perfect. Okay, so all I'm saying is these are the friction coefficients we measured in the laboratory for the same two blocks, even same materials, same conditions, more or less.
Yeah. I have a question on this graph and the previous one.
Yeah.
Is the maximum value here, like the 0.75 or the 0.90, a physical value? In a sense, it would be a shear strength
Um,
in
the
the
0.75 maybe approaches the it's a limiting value from below. So whether we get to 1, we've actually seen shear strength friction coefficients that have approached 2 in some of our experiments. There we get super shear. But it's always going to be the order of the maximum shear stress or shear strength is going to be in the order of 1 or so in our experiment.
But is this parameter a material property or not for you?
Not really. Not really. Once we start to measure, and we're doing that now, the cohesive zone, I might be able to tell you for the materials that we're measuring what the maximal strength is. But I don't think in these, I mean, these experiments are just a sample, but we can go over here, for example, and I don't know what the limit is really. I can estimate it, but, or guesstimate it if you like, by using scaling arguments. But there's nothing special about this value or this value per se. Eventually, we're going to start touching the shear strength, the ultimate shear strength of the material. But for this material, I don't think it's 0.75. It's still too low. Did I answer your question, Francois?
Yes, and I see you have a question from John as well.
Okay.
I'm sorry.
Okay, this is on the previous slide where you look at the velocities.
Yeah.
So if I understood this correctly, which is questionable, you suggested that you can get slow, you can explain essentially slow or fast earthquakes, all with fracture mechanics.
That's correct. Now, I'm not sure all slow earthquakes. Okay. Cascadia, for example, I don't know of this fault, but the statement is, in my experiments where I have a single fault, if I'm very close to the limiting value of if I have enough energy to barely go over the fracture energy, I'm going to get very slow propagation. That's the statement. Now, whether these are silent or slow earthquakes in nature, I don't know. But
it suggests, does it suggest that it's possible that, so people have suggested there's fundamentally 2 different processes, slow and fast earthquakes. This would suggest otherwise, potentially?
This would say that you could explain it, even very slow processes, in a single framework. But I'll be showing you in a second about nucleation, where I see very, very slow fronts that are ruptures that are moving that can't be explained using typical fracture mechanics. So it doesn't necessarily explain everything, but not every, I think the flip side is correct. Every slow earthquake that you see is not necessarily something different than fracture mechanics. I'm not claiming that every slow earthquake can be explained by fracture mechanics, though.
Okay, thank you very much.
Okay,
Joan,
hopefully it's clear. But
Joan and Jay, just to kind of keep a discussion going a little bit. Yeah, so a different, a slightly different way of thinking about it, but exactly the same as what Jay is saying, is that these slow ones are cases where if you had a fault that was just creeping the entire time interseismically, if you will, and therefore building up very, very little strain energy density, when it starts to move slightly faster, it'll have no extra energy to do anything to drive the thing fast. So I think it's saying the same thing that Jay is, but in the context of
that we have the strain energy in the system, just to say what you said in different words or something. There's no extra, there was no overstress. It's exactly supplies the fracture energy along a crack. And if it's exactly, and it's hard to tune it that way. That's why I'm not sure that like all slow earthquakes that you see in nature really are just at the borderline. Because it's a very experiment in the laboratory, it's hard for me to get this. But it can be done. I can also get arrested cracks. In fact, all earthquakes are arrested cracks if you think about it. You never see an earthquake, correct me if I'm wrong, that breaks an entire fault. It's always starts somewhere and ends somewhere. Now, it might be 1,000 kilometers, it might be very large, but it always stops. So arrested cracks or arrested ruptures that we see in the laboratory are in a sense analogous in that sense to what happens along real faults.
So Jay, we have two. We have another. Actually, no, there was two. Now there is only one question by Xiaobing. Please, Xiaobing.
Yeah, thank you. I just have a naive question for your next slide. When you show that the mu_s is fluctuating. Yeah, if I understand correctly, the rate and state law just say the mu_s is not really existing because the mu depend on the loading velocity and the history. So here you're talking about the mu_s. What's your definition or what's your measurements here?
Well, okay, the mu_s that I'm defining here is exactly like the textbook. The shear force applied to the system divided by the normal force applied to the system. Now, rate and state will give you certainly corrections due to aging, due to velocity corrections of the friction coefficient. In these materials, this is plexiglass or acrylics. These corrections are usually on the few percent level. Okay. Now here we're seeing 100% corrections. So I think the corrections here are not because of small velocity dependences, logarithmic velocity dependence or so that's in rate and state. I think it's something else. I think it comes in because of basically fracture mechanics. It's a, you know, I'm throwing it all under one rug, but I can, if given enough time, I can explain what I mean by that. But there is no friction law that's assumed here. If we get it, fine, but there's no, in fact, all of this stuff here assumes no friction law at all. We're subtracting away the residual stresses at the tail of the crack. So we're looking at the stress drop at the tip of the crack. That's why it's delta tau and not tau. Okay, but beyond that, there's only one parameter in this theory, and in this description, it's not even a theory, it's the fracture energy. And with that one parameter, I can explain all of these things. So there's no friction. Now, the friction law could come into describing, for example, what the residual stress looks like. But it's very well behaved relative to this, the initial stress that we're seeing. Is that clear?
Okay, thank you.
Sure.
Hey, Katharina, please go ahead, Val. Yeah.
Jay, I have a question about the light blue event. So it looks like it almost reached some form of steady state. It's a velocity below the radio wave speed. Can you hypothesize what made it do so? Because even if you had a little bit of the excess energy compared to your fracture energy, in theory, in elastic material, it should accelerate, right?
I actually know why it does it. I don't need to hypothesize. Okay, in this particular experiment, let me see if I have a picture. I forget what I've already showed you. Okay, this is good. The static stress intensity factor is given by a weighted integral over the stresses in front of the crack before the crack arrives there. So in this case, it's a global. It's given by the global stresses. Okay, so in this case, the stress distribution ahead of the crack even gave me negative stress stresses that are below the residual stress. And with that, I can get the stress intensity factor, or the energy flow to the tip of the crack actually can go down with the length of the crack L here. So That's basically what happened here. So at some points along the crack, along the interface, because maybe a tilt of the system very slightly or inhomogeneity along the interface, the stress value goes below that of the residual stress. Still, the crack will propagate, and whether it will stop or not, it depends again just on this weighted integral. Okay, is that clear?
Yes, yes, thank you.
Okay, great. And one more question we have?
Professor Shu.
Yeah, Alex, please go.
Hello, Jay. This is Alex from Paris. So I had two questions. I mean, the first one is it possible that the dispersion you see in static friction coefficient would actually disappear at higher normal stress?
Not in our experiments. It actually gets worse.
Ah, okay.
It doesn't disappear.
It's worse at higher normal stress because
the reason is that the stresses are very inhomogeneous.
Mm-hmm.
Even if we have as smooth a interface as we can get, first of all, it's still rough. Second of all, there are torques, there are high points, low points overall. So, and even if we start with a perfectly homogeneous interface, which we never do, once we get an arrested rupture, suppose we're just at this transition here where G equals gamma. Then we're at arrest, we have a stress singularity at the arrested structure, at the tip of the arrested rupture. So even if we started perfectly homogeneous, dynamically we create a heterogeneity in the stresses.
Mm-hmm.
So it's a mess.
Yeah.
Our laboratory experiments are almost as messy as the real fault. Almost, not quite, but
Yeah, because
please go ahead, Alexis. Alex.
When we do stick slip in rocks, we tend to see that the friction coefficient becomes more stable at really high normal stress. But I mean, again, this is I think that was also already pointed in Byerly's paper in 78. The second question is about this the comment of Ekaterina that she just made and that how you answered to it. So you say, okay, you calculate K, which is an integrated an integration of the stress ahead of the crack tip, and that actually and sometimes you even have negative stresses. That actually would mean that in your smooth velocity profile, there has to be very strong fluctuations as well of velocity.
Well, here's the velocity profile. You can see.
But there might be even stronger fluctuations at small scale that you're not resolving there, and so that would have implication for radiation that are important.
That's a great comment because we have, you should get no seismic radiation in a crack. Something like this, you would get seismic radiation here where it starts and where it stops. But there shouldn't be any large-scale radiation. Everything that you're actually picking up is because of rapid fluctuations of the crack tip. Radiation, at least in physics, is because of accelerations or decelerations. So smooth accelerations such as this would give you very little radiation. Anything beyond that, though, would radiate to kingdom come. Mm-hmm. So the acoustic emissions that you're picking up in rocks while fracture is going on are because of inhomogeneities of something, either the stresses or the fracture energy or both. Yeah, thanks for the comment or the question.
But Jay, if I can, on this comment, I would like to ask you to clarify one concept, because in answering to the Ekaterina and Alex questions, you are always referring to something that is ahead of the tip. So to me, the issue here is not only the behavior of the rupture velocity, the way in which the rupture fronts propagates, but also what is happening in terms of sleep velocity around the tip. If in any case, even in this type of simple experiment, you have a cohesive zone, how can you exclude that you have a contribution coming from behind the crack tip? I don't think that you can exclude it because it's not instantaneous. And if you look at the sleep velocity, not only at the rupture velocity, to me, this is a corroborating evidence that you cannot exclude, even in these experiments, what is happening just behind. Therefore, we can discuss the size, how much big is the size of behind. But I would not agree of referring to the stress state only ahead at the tip. Otherwise, you should not have any cohesive zone.
Okay. No, I agree and disagree at the same time. First of all of this picture is without any cohesive zone at all. All of the dissipation is at the crack tip. And in that sense, we don't need to worry about the stresses in the cohesive zone because all of fracture mechanics or this version of fracture mechanics assumes a point like or small scale yielding. So there is no effect of the cohesive zone because the cohesive zone in this picture doesn't exist. Now, in back of the crack, yeah, I mean, we can actually measure a cohesive. We can measure the slip. We do. We even published something at some stage. I can talk about it, but we get a parabolic slip profile behind the crack, except at very near the tip. So we do see the cohesive zone. Now, within the cohesive zone, the material can influence the crack ahead of it, for sure. So I guess the question is, how small is the cohesive zone? And what is the region here that we can, where this singularity is blunted, is regularized? So I think that's what you're saying, no?
Yeah, but this to me is a strong limitation to extrapolate. So everything you said is perfectly coherent in terms of linear elastic fracture mechanics and also interpreting the propagation of a frictional instabilities as in your experiments. Yeah. However, the way in which earthquakes radiate seismic waves is not only is for sure through acceleration, but it is also determined by how steep is the stress release with respect to the unloading curve. And this is depending of the cohesive zone. Earthquakes radiate because the stress drop occur of a finite space on a fitting times, and this the stress rate of weakening rate is determining the capacity to radiate that you don't have here. Because you don't have any weakening rate.
If I would take the fracture energy and add a random component to it, which is basically the contribution of the cohesive zone, because the cohesive zone determines what the fracture energy is, then I would get probably rapid acceleration and deceleration. I think that's basically what you're saying. Here I'm taking it as a constant. Now in our experiments, it's more or less a constant. Certainly it scales where I'm showing the equation of motion. So in that case, it's fine, like for scales such as this. But if I look close to the crack tip and have any heterogeneity, this fracture energy is going to have a random component or a highly fluctuating component. This highly fluctuating component would give you radiation. In fact, fracture mechanics is telling us that, okay, the energy flux into the tip of the crack is an integral quantity. It's all of this, the material around the crack is contributing. The fracture energy, though, is a very local quantity. It's how much energy it costs me to break this point. So if this is fluctuating, has a fluctuating component, I will get immediate acceleration and deceleration. So I think we're saying the same thing. It's just the local piece is in here. It's not in here. And I have a hard time thinking about a large variations in the energy flux and the energy flow to the crack tip, because that's a global, the whole world is contributing to that. But now it's balanced by something that's very, very local, and that's the fracture energy. And that
Jay,
would cause...
To continue the discussion, Jay, you made the statement a few minutes ago that you wouldn't expect any radiated energy, but of course, you show us a plot there of a crack that's moving along at the Rayleigh wave speed, at least on one end of it. So all of the points that are out in front of that crack have to accelerate dramatically, and those points are going to radiate energy when they accelerate, right?
That's already included in fracture mechanics. That's not new. That's a smooth field, basically. That's part of the solution.
But physically, when the crack propagates, there are points that accelerate from nothing to a slip velocity that goes along with the Rayleigh wave speed. So there's nothing smooth about that, even in your experiments, right? There's going to be radiated energy.
It goes into kinetic energy that's radiated out, but that kinetic energy field is very smooth. So I guess my statement is, if you see rapid fluctuations in the seismic energy, it's not because of fracture mechanics. Well, it's not. That would come from Massimo's point, that if the fracture energy is fluctuating, then you're going to have this balance that's all the time. It's all the time having to slow down and speed up the crack in order to satisfy this equality.
Yeah, I'm not talking. I agree with you, but I'm not talking about the variations and I'm just talking about the energy that's going to be associated with accelerating those points. Now, it could just be a constant energy. Maybe that's,
No, it's very smooth, is all I'm saying. Okay. You will get acceleration because the cracks here, I guess, where is it? These are accelerating. Okay. So you will get you will get energy that's the energy density, the kinetic energies, the energy causing the separation of the two faces of the crack. That's kinetic energy in the bulk. And that's like a global thing, that it's not just the faces have to move, but everything around it has to move to accommodate that.
Right.
And that's the kinetic energy field that a crack is giving rise to. But it's very smooth because it's a kind of a global thing. So yes, the point right ahead of the crack goes from 0 to 100 instantaneously.
Yeah.
But that's not causing the radiation is caused by the whole crack itself, the moving stuff in order to moving stuff around in order to accommodate that. Okay. So it's a little tricky.
I don't think we disagree. I will say that you should stop us. You've been very successful at getting us to participate. And
okay.
If 20 minutes is enough, then great. And otherwise, tell us to shut up.
Okay, I am going to get to the nucleation right now. Okay. Nucleation of the crack. So, okay, here's the question that we're trying to answer. So something is missing here. We have this wonderful description, fracture mechanics, but in order for fracture mechanics to describe a crack's motion, we need a crack in the first place. No crack, no fracture mechanics. So the concept of nucleation is asking, how do we get the initial crack? So how does this initial crack form? And how does it reach a critical length where the crack takes off? The Griffith length for the expert. So pictorially, we start all of our experiments with a random contacts. And somehow, after nucleation, we get a front. So how do we start? What lights the match to start the forest fire, if this is the forest fire? So that's the question that we'll be looking at in the next few minutes. And here, to show this more graphically, I imported a Hollywood actor, so if you'll bear with me, here we go. Okay, so this is just an explanation of what I just said. Put a little crack in. This is what I explained, but what creates this initial crack? I tried to get Robert Redford, but he was busy. Okay, so this is what we're going to talk about. Now, what's the experimental problem in doing these experiments? Is because in general, we can't predict where and when nucleation is going to take place, even in the cleanest experiments that we can make, certainly in our laboratory. So our solution is we're going to utilize fracture mechanics to control where nucleation is going to take place and when it is. And actually, I'm rewriting history because we discovered this totally by accident, of course. Okay, so I'm going to show you that. So what we're going to do is I want to study nucleation at this point along the interface. So what I'm going to do is put a speed bump here. I'm going to increase locally the fracture energy. I'm going to generate a usual rupture that's going to start somewhere here, going to barrel along. And when it hits this speed bump, if the energy flow into it is smaller than the level of the fracture energy, it's going to stop on its nose. So we're going to do that in a second. And then what do we get out of this? We get a very well-defined stress profile. So we have our stress singularity where it stopped. And if we nucleate somewhere along here, and we know where we can nucleate on the other side of the speed bump, we know exactly what the stresses are at which it causes. So we know it's going to nucleate here eventually. And when it does, we know what the stress level is. And we're going to use that to describe the nucleation process. So this is a picture of what we actually see. So here's an arrested crack. This is a blow up of 40 millimeters of a 200 millimeter region. So we have a crack that's barreling along at probably a large percentage of the Rayleigh wave speed. It hits this speed bump and it stops on its nose. And then we wait. This is our barrier here. This is where the speed bump is. And on the other side, if we wait long enough, we see slow nucleation takes place. And we have all the time in the world, since we know where it is, to study it. So that's what we're going to be talking about. Now you might ask, okay, what do we use to make the speed bumps? Okay, a magic marker. So all we do is this is a picture of a transparency pen, and we make a mark a millimeter wide along one of the frictional interfaces. And the reason we did this initially is that we wanted to study the slip along the interface. So we're going to make an array of these marks and watch what they do. But when we started to do these experiments, we noticed that cracks would barrel along, and just when we wanted to see what's the motion, it would stop on its nose, until we figured out that what we were doing with the magic marker is increasing the fracture energy. So we can measure the effect of we're actually increasing the fracture energy by a factor of about 5 with your standard transparency marker. So now we're going to use this to study the nucleation process. So this is a cartoon of what we'll be looking at. So we have a number of stick slip events in the same experiment, so under the same conditions. I've labeled these by some of these, and in all of these have a different nucleation time from the moment that the initial crack arrests. And what we find is the faster the arrested crack, so the more energy it's carrying, the shorter the nucleation time. In fact, this is what it looks like. So this is the nucleation time in milliseconds relative to the arrest velocity of the crack. So the faster the crack is going, the shorter time we have before nucleation. But we're going to use, again, fracture mechanics in order to describe exactly what's going on in this process. So fracture mechanics isn't involved in this process except to set the stage to do the experiments. I'll show you what I mean by that. And we also have cases where we're barreling along, we stop, and then we could wait forever forever is seconds in our experiment, and no nucleation takes place. And you can see kind of here that the waiting time that we need for nucleation is asymptotically going to infinity, if you like, at least experimental infinity. Now, I'm going to go through this fast, so just bear with me. So when this crack stops, it actually broadcasts a shear wave ahead of it. It changes very slightly. This is a blow up of that, the fracture, the contact area. And this is on the level of like 1 or 2%. And that's actually the trigger for the nucleation. So the idea is that we're sending a high amplitude wave ahead of the arrested crack. And that's breaking, I think, the weakest points of contact. So the weak guys are being broken. That's the only reason that we can see this front. And it kind of disappears as it goes within a few millimeters. We can't see it anymore. But that's the match that's gonna start the nucleation process. So if we look, for example, at the change in the contact area, and here it's a change, the whole scale is 4% change. Okay, so we're changing by 1 or 2% here. And we'll call this the damage zone, if you like. We'll give it a Greek letter Xi in order to make it look scientific. And now we watch as Xi unfolds. So this is in the initial damage, and now we're looking as a function of time. And every once in a while, I'm going to show you a snapshot of the 2D fracture area here. So in this case, we nucleated near the side. This gray thing is the barrier. And now it's going to propagate. You can see it gets larger and the center is moving. It's going to propagate until it gets long enough in this red to actually cause fast rupture. And then it just goes like a bat out of hell. Okay, so we're going to look at this process that gives rise, it basically creates the initial crack that then in red causes the rupture. So this is this particular experiment. So this is the length of this region of reduced contact area. So over here in blue, this is this damaged part that doesn't move very much. And this is the slow motion of this nucleation front. And this red point is where dynamic fracture takes place. All the stuff that I've talked about until now. Now the nucleation front, this is both in, you can see here, it's both in X and in Z, but they follow each other. So I'm only going to talk about the nucleation dynamics in X. And these are really, really, really slow. So these are moving along in our experiments at the meter per second region. This is not the slip velocity, this is the rupture velocity. So it's 3 orders of magnitude smaller than what's going to develop eventually when the crack starts to rupture, when the crack starts to go dynamically. So these are aseismic, if you like. These are aseismic nucleation patches that expand, and they expand at nearly a constant velocity until they reach a critical length, and then earthquakes explode. So, and these also have a time scale, the same time scale that I told you about. It's the start of the rapid rupture. So what determines the time scale, I'm going to go through this fast, but hopefully this is clear, is the stress at the point of nucleation. What was that, Chris?
Okay, there's a Jean-François, you just unmute.
Yeah, thanks, Jay. Just quick question. How do you determine Xi, this length scale? Because you have to set a threshold, right? And depending on the threshold that you choose, how sensitive is the result that you get?
Well, our threshold is basically the noise level of our contact area measurements. So we chose like 1 sigma over the noise area, over the noise.
So it's within 1% of A over A naught equal 1, let's say.
Yeah, yeah, even less. It's about 0.5%, because that's the noise level of this. And then anything over that, we mark it as something. Okay. All right. And then we just look. I mean, basically, it has this form. So over here, these fluctuations are our noise level in the system. And these are significantly above the noise level. So we can, I mean, the fact that we can, I forget where this thing is. Okay, well, we can see this fast rupture taking place. It's not a rupture, it's like a high amplitude shear wave. That's in this 0.5% thing. So yeah, it's pretty well defined. We can change the threshold, and it doesn't change really anything. Not the dynamics of what we're looking at.
Thanks.
So, okay, now as we can use the magic of fracture mechanics to convert the arrest velocity of the initial crack to the stress of the arrested crack. So forget the details, but using the formalism of fracture mechanics, we get this mysterious K. And we define sigma induced, or this is the induced stress at the point of nucleation. R star is the point where the nucleation started. So using this, we know precisely what the stress is at the nucleation point. And then for a given experiment, we can, or a given run of experiments, so these are like 10 runs at different initial arrest velocities, inducing different values of the stress at the point of nucleation. So we find that this is 1 over the nucleation time is more or less linear with the stress that we measure, or we measure it at the point of nucleation. Now, we also find that there's a threshold stress. So below some critical value, which is dependent on where the nucleation takes place, we won't see any nucleation at all. The crack, and this is an example, it'll just sit there. So, okay. We can talk about the onset length. So this is a movie of the patch that's nucleating as a function of time. When it gets to tau equals 1, which again is the time scale where dynamic fracture takes place. I'll show this again because it's kind of a neat movie. Then it explodes. But all of this part is the patch is slowly increasing its size. When it gets to a critical size, boom, then we have rapid rupture. So this is the rupture onset at this point. What's interesting is at this point, we can compare the length of the initial crack to the Griffith length, or the length that fracture mechanics would tell us that a crack should accelerate or should lose stability, and that's these red points here. So pretty close, we find that the Griffith length, the end of this patch, when it gets to the Griffith length, then fracture mechanics takes over, and everything that I've told you until now takes place. What's interesting is that this Griffith length is orders of magnitude smaller than predictions, for example, of the critical nucleation size, using, for example, the theory developed by Onishi and Rice, and certainly rate and state predictions for these materials. So the rate and state would tell us that it's on the order of hundreds, if not 1,000 millimeters, and here we see 4 or 5 millimeters for the. So this is a very different scale than typical nucleation scales in the literature. I'm almost finished now, so I'm going to go through. Okay, now for a given place, okay, this is a movie of what I just showed you. So these are different snapshots at different percentages of this critical time, so 0.6, 0.7, whatever. And that's at this point in the graph. So each one of these points is the development of one nucleation patch. But I can go to like a point here. In fact, I will. You're 3 different points. And if I normalize the contact area measurements by this critical time for rupture to start, I find that all of these, the rupture patches, they behave in a self-similar way. I see the same thing in all of these experiments. Once I normalize the times by the time it takes to rupture. Now, is there anything very deep in how these patches look? Not really. Because, okay, these are for, I don't know, the magic marker, we put it 70 millimeters. If we make it at 100 millimeters, we see the same self-similarity, but the patches look different because the local topography is going to be different depending on where I stuck the marker. Now, if we say, okay, do I have like 5 minutes, Chris?
Yeah, for sure.
Okay, great. So this is a stick slip sequence. So this is in blue, the same kind of stress variations or force variations that I showed you earlier. And at the same time, I'm looking at the mean area of contact along the patch that we're looking at. And you can see that it goes down, it goes up, and all that stuff. Why I'm showing you this is that the topography, now I'm looking at the contact area, but not normalizing it by anything. The topography, even though I'm looking at 30 earthquakes that are taking place between this event and this event, actually the topography doesn't change. I have a rupture front at this location. It doesn't erase the contacts, the contact profile that I'm seeing. Basically, if I have like a tough spot, a high ridge like we're showing here, that ridge is going to stay even though I have a lot of ruptures that are going over it. And if I have a low spot, the same. Now, sometimes, for example, wait, there was some reason. Okay, some things do disappear, small features, and these small features actually could change a lot the dynamics. So, okay, let me stop here. I see we have a question. Katerina.
Yes, Jay, so it looks like you consistently get nucleation a little bit off of where your marker line is, not right at the stress concentration. Why is that?
Wonderful question. The definition of a wonderful question is I'm going to answer it in the next slide. So hold on for just one moment. So the question is where the nucleations, where these ruptures nucleate. So this is the normalized contact area that I was showing you, and we see the patches that I showed you in various movies. And this is the non-normalized contact area, and this is the answer. Locally, we have a weak spot, and that's where the nucleation is going to take place. Now, why is it this weak spot and not this weak spot? Because this weak spot is closer to the stress singularity here. So I have higher stresses at this location than I do at this location. So that's why I'm looking in this area to, and that's why it will take place. Now, if I follow then the nucleation patch, it will follow the topography of the ridges and the cold and hot spots of the region. So as you can see, this is nucleating and is being guided by this ridge of high fracture energy barriers here until it gets through the barrier, and then it expands rapidly until it explodes. So did that answer your question?
Yes, thank you.
Okay, thank you for the question. Now you might ask, okay, why here than here? I have no idea. Sometimes we do get, often actually, we get nucleation at two patches. So I'm showing you the simplest cases where just one, there's the one weakest, apparently this spot is weaker than these spots. So, okay. So now just to summarize. So I've shown you that the onset of friction in our experiments is basically dynamic rupture. And then we ask the question, how does the rupture start? And we've shown that, okay, once it propagates, fracture mechanics is relevant. When it's nucleating, actually, this is not standard fracture mechanics. Why? Because there's no acceleration, even though the patch is expanding, and it's very, very, very slow. So right now, we're in the process of trying to find an explanation for this. I'll share it with you. I guess, in another year or so when we finally decide what we think is happening. But it's not standard fracture mechanics. Standard fracture mechanics, as of crack, gets larger, the energy flux or the stress intensity factor at its tip will increase with its size. So we should see rapid acceleration. And here we're always seeing very slow propagation and more or less constant, steady propagation. So we're in the middle of looking at what is the driving mechanism for this nucleation. It is a critical phenomenon. There's a critical stress that beyond which the time that it takes for this nucleation to go is proportional, or the inverse time is proportional to the stress at the location. And I just shown you kind of a quickie example that the evolution actually depends, the details depend on the local topography, but all of these different locations actually have the same overall formalism here. This is the same qualitative description. So I guess a bunch of take-home messages. One thing I've told many times, in fact, probably most of you are tired of hearing me say it, friction is fracture, at least to some extent. We have real honest-to-God shear cracks that propagate within frictional interfaces. Now, there are some caveats that Jean-Francois can tell you. He and Eran Buchbinder have shown under what circumstances we would expect shear cracks to happen. But basically, as long as the residual stress is more or less constant, behaves well, we would expect dynamic fracture, fracture mechanics to be relevant. This paradigm for friction is very different from the classical view, Fine. Instead of a force balance that's inherent in a friction coefficient, basically fracture mechanics is telling you it's an energy balance. Very different, but I won't go into it because we went into it enough anyway. And nucleation fronts, if we understand them, well, even if we don't understand them, they replace the idea or the concept of a static friction coefficient because they provide the initial crack that when it gets long enough, then fracture mechanics takes over. So this is the way that we go from zero crack to some initial crack. And it's a new entity that's not described by standard fracture mechanics. And that's all I have to sell. I hope I didn't waste too much time, but thank you for your attention.
Fabulous, Jay. Please unmute and join us, me, and thanking Jay for a fabulous talk.
Good.